All right, let's get to the next part here, just name distributions. You know what a density function is now. There are lots of density functions that we use that have particular names. It's a lot easier to say something like, I think age has a normal distribution in my population, than it is to write out the whole population data set. So when we say normal distribution, that's just a shorthand for a particular density, and in this case, the standard normal distribution. When we say that, we just mean that the density function for whatever variable is that we're describing, big X, has this particular form. The important thing here is e to the minus x squared. That really is what gives this its characteristic shape. And what that means is that it's the x squared does two things. One is that it's symmetric. So if I put in a -1 for x, the -1, since it's squared, becomes a +1. If we put a -2, the squaring makes that it's the same. -2 squared is the same as +2 squared. So we get the same value. So it makes it symmetrical across 0. And the square also means that it decays very quickly. In fact, more quickly than e to the minus x than exponential decay. So it's just like a doubly exponential decay. So it means that there's very little probability in the tails. This random variable is very tightly concentrated around 0. Why do we give this distribution a name? It comes up a lot in statistics. And so it has this particular density function. It seems a little weird. What is it doing? And you know, this square root of 2 pi, these numbers basically are just there so that the total area under the curve is 1. Again, the important part is e to the minus x squared. And it so happens that you're never going to find a variable in the population that is actually normally distributed. You'll find stuff that's close, right? So like, you know, maybe you think height is roughly normally distributed in some population. But even then, not really, because, you know, maybe if you split up the population by chromosomal sex, then maybe, but jointly, you know, maybe you're going to have 2 peaks, right? Even then, if you're just looking at, you know, chromosomal males or something like that, is the distribution really normal? No, because everyone's height is greater than 0, right? And the normal distribution, in theory, it goes off forever, right? There's some positive probability that somebody has, if it were normally distributed, no matter where you would center it, there'd be some positive probability that people would have a negative height, which is simply not possible. It doesn't make any sense. And so no measurement is actually normal. But the reason it comes up a lot is not because when we're talking about population of individuals, that measurements are usually normal or even approximately normal. That's almost never the case. It's because measurements taken in populations of samples can be theoretically shown often to have limiting normal distributions. So if you remember, again, last time we were talking about taking samples from a population and having the population of all possible samples. So I could sample like 1,000 people, and then I can sample a different 1,000 people and a different 1,000 people with repetition, and then have a lot of all the possible samples I could get. If I take like the mean height in each of those subsamples, I can show mathematically that as the size of all those samples grows to infinity, that the mean height has a limiting normal distribution. That is my statistic, my average that I calculate from a sample, which is a characteristic of each sample across the population of samples, that is normally distributed in the limit. And so that this becomes a very, very, very useful tool in a lot of settings, and we'll see much more about that later. I just want to motivate why this particular density, it just happens to be what a lot of things end up looking like when we start doing statistics. It comes up a lot. Notationally, the way that we write that something has a particular distribution, when that distribution is named, we say the random variable that we're talking about, so in this case x, we do the little tilde. The tilde says this variable has this following density in my population, and then we write the name of the density. So here, since the normal distribution is so common, it's abbreviated most often to n, and then the 0, 1 indicates some parameters. We're going to talk about that in a little bit, but if you see n, 0, 1 is the standard normal, what we call the standard normal distribution. So here's another distribution, which is the standard uniform distribution. This density is 0, except for on a particular set of values. and here it has the value 1. So in this case, it's 0 everywhere, and then 1 on in between 0 and 1, and then again 0 beyond that. So what this means is that the relative likelihood of any two values here and here is the same. So this kind of represents the situation when somebody says pick a number between 0 and 1. You usually imagine that you're picking uniformly at random, that is, any two numbers have equal likelihood of being picked. That's what this density represents. It comes up a lot also. It's a very intuitive notion. So it gets its own name, uniform distribution. So we write x tilde uniform on 0, 1. That's saying x is a random number between 0 and 1, where all numbers between 0 and 1 are equally likely, and any number less than 0, any number greater than 1 is not possible, or has probability 0. Another super common one is the Bernoulli distribution. The Bernoulli distribution represents a coin flip. It's kind of unfortunate that it has like such a cryptic name, like Bernoulli. It's the name of a guy. Like I mean, it should just be called coin flip distribution, honestly. But you're gonna see it. So we're gonna tell you what it's called. Oh, by the way, speaking of guys' names and stuff like that, in the normal distribution, you'll also see it called Gaussian distribution, because there's a guy, Gauss, who does stuff related to this. Or you'll see it called the bell curve as well, but that's all the same. So going back to here, the Bernoulli distribution is just a coin flip. So it's a discrete density function or a probability mass function. It has value 1/2 at 0 and 1/2 at 1. So we're coding the result of the coin flip. Tails is 0, head is 1, and it has 50% chance of being each of those values. So it looks like this. And we'll often write x tilde burn 0.5. You'll also see sometimes something called binomial. Binomial is a distribution. A binomial distribution is basically the sum of a lot of coin flips. You're asking, like, if I flip 20 coins, how many of them are heads? So sometimes you'll see binomial used when people really mean Bernoulli, where they'll say binomial of one coin flip being the Bernoulli, but you know, it's I think usually clearer to just say Bernoulli instead of binomial 1. So these things exist in R. You don't have to like calculate what, for example here, what this value is by hand. You can just say, R, tell me what the value of the normal density function is at x equals 5, right? And it'll tell you. So the way that you ask it to do that is you say d norm. So d stands for density. So if you want the density of the normal distribution, it's d norm. And d, it isn't doing anything special. It's just they happen to consistently name all these functions d whatever, d norm, d uniform, d binom, so that they all kind of work the same way. So normal is d norm, and it has a couple inputs. The first one is x, so what's the value that you want to calculate the density at? And then these two, mean and SD, we'll talk about later, but uniform is the same, and then the Bernoulli, R doesn't have Bernoulli built in, that's binomial, so you have to say d binom x 1, and then you know, here we'll talk about this in a minute, but 0.5 is the default value there. So R has these all, and you can see here how you can plot one of these density functions. So this is a common idiom for how to plot the graph of a function that you should be aware of and use. So the first step is to generate a sequence of x values. So that's what this does. So this generates 100 x values between -5 and 5. So like -5, then -4.9, -4.8, dot, dot, dot. Okay. Then you calculate the value of the function at each of those values and generate the y values. So if I were to plot this with gm_point, you would see that this is actually really like a bunch of little points like this, right? And then geom_line, all we're doing is connecting those lines with little line segments. So in fact, this is actually like a piecewise linear approximation to this curve. That's all. So this is a generic way. If with any function, you can plot it like this by first generating a sequence of x values and then finding the y values and then connecting the dots. That's what ggplot does when you do geom_line. You can also calculate using R. There's an easy way to get the area under the curve. You have to use these p functions corresponding to the d. So p stands for probability because you use them to calculate probabilities. For example, if I want the probability that x is between -1 and 2, right? I know geometrically or graphically that corresponds to calculating what the area under the curve is between -1 and 2. So the way that I do that in R is I call p norm at 2, and then I subtract off p norm at calculated at -1. This p norm, it's actually a thing called a cumulative distribution function, or CDF. It's a very important concept also in probability that I've chosen to kind of omit from this course. But if you go and look at all of the readings, it's discussed at great length. Really what this is doing, the reason that it's subtracting is because it calculates, this p norm function calculates the area under the curve from like basically -infinity all the way to here. So the area, this little area here is all of that area minus this area. That's why it looks how it does. But you can see you can get exact area under the curve like that. Okay, so many distributions have what are called parameters. And that's because when somebody says normal distribution, usually they're talking about a specific normal distribution, but there's actually a whole family of normal distributions. So parameters, that is describe families of distributions where all of the distributions in the family have roughly the same character or like the same shape, but they're each slightly different. So for example, for the normal distribution, the parameterization lets us say that we can shift it over by a certain amount and we can spread it out by a certain amount. So the shifts are described with this parameter often called mu or mean, because we will see that it actually represents, for a variable that has this distribution, this value is in fact the population mean of that population average of that variable. So that represents kind of where this peak is. The other parameter is sigma, which represents how wide this is, and in fact corresponds to the population standard deviation of whatever variable has this distribution. So the full normal, any normal that has mean mu and standard deviation sigma, the density is this. So you can see that it's still, basically a minus x squared. It's just shifted over and then scaled, and then in the constant out front, to make the whole thing, the whole area under the curve equal to 1, you also have to scale by that. By the standard deviation. So here I'm just giving you some examples of normal distributions that have different locations and different widths, right? But all these are normal. They have fundamentally the same character. But of course, when you're describing, you have to say which one you're talking about. And so you have to say what's the value of mu and what's the value of sigma. So if to say that x is a normal with values of mu and sigma, you write it like this. So this would be writing a generic one where maybe you don't know, or you don't want to specify what the mu and sigma are. You just write mu and sigma symbolically like that. But if you know what they are, you would put numbers here like 0, 5, right? Okay, so a little brief conceptual problem. Let's say that I have a population of HIV positive people, and I'm interested in the CDC4 cell count, which is a measure of like strength of the immune system, I believe. And I believe that the distribution in my population of CDC4 cell counts is uniform between 1,000 and 1,500, whereas my collaborator thinks it's uniform between 500 and 2,500. And we go out in the world and we sample some people from this population, and we found someone that has a count of 1,750. And my question is, what does that mean about our hypotheses? So just think about that. All right. So the fact that we found someone with a CDC4 count of 1,750 invalidates my hypothesis, because I think it's uniform between 1,000 and 1,500, which means that I should not expect to find anyone with a count greater than 1,500 and anyone with a count less than 1,000. So this is not correct. However, it doesn't mean that this is correct, right? Because it could be, I don't know, some normal distribution, or it could be some other thing that I haven't described to you that doesn't have a name. Most likely that. But certainly it means that this is out of the question, right? So let's say this is the histogram of counts that we got from our samples. So I just want you to play with dnorm, plug in different values. of mu and SD to see if you can plot a density that looks like a good fit. So back here, when I was showing you how to calculate the value of the density at a particular point, I said ignore these things for now. Well, now we know what they are, right? So these things actually correspond to the values of the mean and the standard deviation that we want. So in R, if you want to specify them, you just have to put values, optional values for these two arguments. If you don't specify them, this defaults to 0 and this defaults to 1. So let's just solve this problem. Let's just copy my code here. Okay, so this is, we want a density that looks roughly like that. So if we just, sorry, we'll get back to this. Okay, so if we just run this, we get the kind of bell curve that we expect. This looks nothing like what we want because, for one, look at the x-axis. We're going from -5 to 5, but here the x-axis is like 500. It's kind of small, sorry. It's like 500 to like 1700. So let's change that first. So let's go like 500 to 1700. Let's start with that. Okay, so obviously we can't even see our peak because our peak is way at 0. So we have to change where the mean, where our peak in the normal is. So let's put it roughly, I don't know, let's say like 1200 or something like that. So we can say here mean equals 1200. Run that. Okay, so now we have the peak there. Obviously, this is still quite different because here this is very spread out and this is very pointed. And so if we want this to be more spread out, we have to change the SD from the default value, which is 1, to something much bigger. So if we try 10, you see it gets bigger. That's maybe not big enough. So let's try like 200. Okay, so that looks pretty good. If I'm looking at like the value around 600, you can see we have a couple people. And here it seems like there'd be a couple people around 600, but not really by the time we get to 500 or like 1700. So maybe something like this is close. Maybe that's as close as we're going to get. We're not getting too much closer than that. And obviously that still doesn't really look like what this does. So do you think that that's a good model or not? Well, it depends what you're trying to do, right? But I think the lesson is that obviously this is just a sample, right? You don't have the whole population. You don't know what the actual population histogram looks like. Maybe it is normal, right? Maybe you got unlucky with this sample. But certainly, 1,000 people is enough, perhaps intuitively, for you to think, okay, if it really were normal, it wouldn't look this kind of skewed, right? Or maybe you wouldn't see two somewhat clear peaks. So, of course, all of this can be made rigorous with statistics, and we'll kind of get into that a bit later. Or you can look up kind of how to test if a sample is drawn from a fixed known distribution. But I think that here, just kind of eyeballing it, you might be skeptical. Okay, so in many stats probability classes, you talk about Poisson distribution, exponentials, blah 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 blah. All these distributions, and it starts giving you this idea that like that's the universe. That is not the universe. Reality is not that. None of those things really exist so much in the real world. Most of the time, it's some really crazy, messy thing. Your population is not even well defined usually, so even defining the distribution is weird. So these things are just tools to help you think. Nothing is normally distributed. They are useful for simulating data. They're useful for doing math because oftentimes you can show, like I said, that things have limiting normal distributions in large enough samples. And so they're useful for calculating approximations and all of that. But you should never really be thinking that something has an exactly this or that or the other distribution that is known.